In the last video, we took a look at forces that cause circular motion, but these were all horizontal circles. Let's take a look at some examples where vertical circles come into play. And in this case, gravity and the normal force will both play a role in providing centripetal force. And we'll take a look at the special case of just making it. So what I mean by just making it is shown in a video of a car doing a loop-the-loop, which is an interesting stunt. And let's take a quick look. So here comes, there's a steel ramp that has been made in the shape of a circle. And I'm going to bring it back to the point where I think that's it. Oh, yeah, that's pretty good. So where the car is at the top of the ramp. Now it's still in contact with the ramp, but it's also executing a circular motion. That's a little bit different. This is not circular motion at a constant speed because the car is naturally going to slow down as it goes up. And I think it's kind of interesting the choice of the vehicle that was used for this stunt. Just a super mini, not really a big muscle car or anything like that. So it's impossible for the car to maintain its speed on the way up. So it slows down quite a bit, and we'll talk about the nature of that slowing down in a little bit. But one of the things that we know is that gravity's pulling it down, and how come it doesn't fall? That's one of the central ideas. So I'm going to stop sharing and we'll come back and take a look at this example. Down at the bottom, we have two forces acting on it. So we have the normal force and we have gravity. But at the bottom, they oppose each other. Now, if this was just a car zipping along, then these forces would be supposed to be gravity. These forces would be equal to each other. But as soon as we enter the loop, now it's going to execute circular motion. And the implication is that the centripetal force is going to be upward because centripetal means inward. Then up here at the highest point, gravity is pulling down. And the normal force is pressing inward. And at the top, since it's circular motion, inward means down. Right, so let's take a look. What's going to result? These are the only two forces acting on it. So in order to provide the centripetal acceleration, the normal force has to be bigger than gravity. So Fn has to win in order to make the centripetal force upward. But in this situation where gravity and the normal force are working together, then the normal force doesn't have to work as hard. So let's take a look then at each one of those in a little more detail. So at the bottom, when we do Newton's third law, F net equals ma. The causes of the force go on the left-hand side of the equation. What the mass is doing goes on the right-hand side. So the normal force is pulling up, so that's a positive Fn, and gravity is pulling down, and centripetal acceleration is inward. So that's going to be plus mv squared over r. So if we solve for the normal force, we'll add gravity to both sides. And then what the normal force has to do is it has to provide a force equal to the object's weight, all on top of the force needed for circular motion. This is one of the examples of a non-inertial reference frame, where it appears like there's an extra force acting. So we're used to the normal force indicating our weight, but here the normal force is bigger than our weight. So you would feel heavier than you actually are. At the top, same breakdown. If net equals MA. And now everybody is downward. Everybody has a minus sign. So Fn and then since the centripetal is inward at the top, inward is down. Minus v squared over r. Now, if we're going to solve for the normal force, we can multiply through by -1 and then subtract Fg from both sides. And that's interesting. So let's factor out m and see what happens. Yeah, let's take this and develop it a little bit more. So now what happens is that the normal force doesn't have to work as hard. And you would feel lighter. So if we expand this a little bit and we want to take a look at three possibilities that could happen with this v squared over r minus g. Well, in the first case, let's suppose it's positive. So let's suppose v squared over r minus g is a number greater than 1. Or in particular, let's just take a look and see what happens if v squared over r is greater than gravity. So what's happening? Well, that means the normal force is going to be positive. So if that's the case, that means the normal force is actually pushing upward on the ramp. Or if this was a Ferris wheel, you'd have a tendency to be tossed out of it. So this would be what we call pulling negative G's. And if it's equal, this is our condition for just making it, where the normal force is equal to 0. And if v squared over r is less than g, then the normal force is inward. The case where the net force is equal to 0, so we often see this show up. This is the quote, just making it. So we could replace this track. We would replace this with like a mass on a string or something like that. And so it makes it over without the string going slack. So just making it means that the normal force is equal to 0. And you would feel weightless. And again, that happens when v squared over r is equal to g. Right, so that could be used for artificial gravity. It could be used for, sort of like a Ferris wheel where you feel weightless at the top. There are all sorts of examples like that. Okay, good. Well, I hope that helps, and good luck on your homework.